Okay, well, this is the Project 4 Pintos Virtual Memory Design Guidance discussion. And I know it's been, um, people have been looking forward to this discussion. I hope that it helps. And I realize that it is toward the end of the first week of the virtual memory lab. So next year, and this is all because, of course, we also, like I was mentioning, dropped a project from CS124, and that has shuffled the lecture sequence a little bit. So next year it'll be even better timed, but this year it's better late than never, I suppose. So let's go ahead and dive into this. Project 4, as you all know, is implementing a disk-backed virtual memory for the Pintos operating system. It has extremely limited support for virtual memory. In fact, it does basically the minimum necessary for virtual memory to implement a user process address space isolation and program loading, but it really doesn't do much more than that. So you have a number of tools that you can rely on, as I mentioned here on the slide. You have a swap partition that you can create that you can basically just treat like a block device. And so 4 kilobyte pages, you can just go in and divide the swap device into chunks of 4 kilobytes. You don't even have to worry about bad blocks or anything like that. You can assume that all the blocks are good. You can use a bitmap to keep track of which swap slots are available in your swap. And it's really great. You can do this all in memory because, well, what happens if the OS crashes? You can't assume anything in swap is still useful and your bitmap goes away. So it's fine. It's like every time you start up the operating system, you assume all swap slots are available. You initialize your bitmap to indicate that all slots are available. Off you go. So that's a nice thing about this. You can be super easy when it comes to the swap implementation because of that. As I say, you can also rely on the existing Pintos synchronization mechanisms. You don't have to build any new synchronization support for this project. Project 5 requires you to build a read-write lock, but in Project 4, you don't have to do that at all. Okay, all Project 3 tests, so these are the system calls, should continue to pass by the end of this project. Now, some of you may be saying, what about multi-oom? Multi-oom kicked my ass, and multi-oom is certainly a hard test to pass every year. A lot of teams struggle to get multi-oom passing. And what I would say is just look at how much it's worth. It's not worth very much. I think it's worth 4% if I remember correctly. Don't quote me on that, but you can look at it. And if it continues to run in projects 4 and 5, it's certainly worth very few points. So that's something that you don't have to worry about. Okay. Yeah, and there are new tests to exercise the Project 4 functionality because there's new system calls, there's mmap and munmap that you have to implement, and there's a few other details that have to work properly when processes shut down and all of that kind of stuff. So there are a few new tests for Project 4's functionality. Okay, requirements. You have to implement demand paging for program binaries, and this is pure demand paging. So while a normal operating system might prefetch the first page or the first few pages of a program binary so that it starts running quickly, we really want you to do pure demand paging in your implementation. You implement demand paging for stack pages. It is strongly encouraged that you have the first stack page already allocated. The reason why we like to do this is because that's where the command arguments go, and it's just easiest to set that up and leave it in memory as opposed to setting it up, writing it to swap, and then setting up the page, the supplemental page table to say, hey, this is where the stack comes from. So it's easier to just do your first stack page when you're setting up the user process like you already have. And then as you fault out of the stack, because the stack grows out of the first page, then you demand, you allocate new frames for the stack to grow into. Okay. Support for memory map files. So memory map regions in a process that cannot overlap. I'm telling you, this is so much nicer than real mmap. the Pintos mmap, you map the entire file into a contiguous sequence of addresses. And so you can think of that as a contiguous sequence of pages, and they're not allowed to overlap with other files that are already memory mapped into the process's address space, so you don't have to worry about any crazy hinky behavior like that. Also, if two processes map the same file into memory, you don't have to worry about what each one sees when the other one writes. This is hugely simplifying, because if you have process A and it writes to a file that is mapped into its address space, and process B has the same file mapped, you don't have to see process A's changes. Real operating systems have to do that because this is used as a communication mechanism in many Unix system programs. But you don't have to worry about that. So you can do this very straightforward implementation to support these simple versions of what operating systems provide. So that's nice. And keep these simplifications in mind, because you can take advantage of them to keep from having to think too hard in your implementation. Also, Pintos does not have shared libraries. All the binaries are statically linked against the library code that they use. So the binary is self-contained, no shared libraries, no dynamic linking, no little stubs that have to be updated by a dynamic linker at load time or any bullcrap like that. And you also don't have to worry about user space malloc. So there's no heap that grows. The only thing that can grow is the stack. So this is hugely simplifying as well. Okay, I see a question here. So when either of those processes are evicted, they just both write to the same file, or whoever wins. The way that these systems usually work is last writer wins, because last writer gets to clobber whatever came just before it wrote. So that tends to be how these systems behave. Just keep in mind, the tests aren't going to exercise stuff that behaves weirdly. This is one of the things that you should always assume in your classes. If an assignment says this weird ass behavior is allowed, you can infer from that there aren't going to be any tests that exercise said weird ass behavior. Okay, so it's only in situations where the behavior is well defined that you really have to make sure that your implementation satisfies that behavior. In these other situations, and I expect that probably your implementation will just exhibit this last writer wins type behavior. Okay, so hopefully that answers that question. Let's see, requirements. Concurrency. What you will notice is, like, Pintos gets more and more challenging from a concurrency standpoint as you work through the course. And so this project has a slightly stronger concurrency requirement than the previous two projects, but it's still not that bad. If a page fault requires I/O to resolve, it shouldn't block other page faults that don't require I/O to resolve. That is a pretty straightforward requirement to satisfy, but it still has enough nuance to it that we want you to think carefully about it. Now, how do we test this? We can't. And you should know that. We will try to evaluate this by inspection. So as I'm sure you all have done in math classes and so forth, where you're like, I don't understand, and you just kind of, I took classes like Math 2 and what you all now call ACM95. I took those kinds of classes when I was an undergrad, and I would just try to do my best and see if I could convince the TA I knew what was going on. I mean, we're going to check this stuff by inspection, but we'll do our best, but you may be able to slip a few things by us, and we won't fault you for that. But anyway, just try to satisfy this concurrency requirement if you possibly can. Okay. The big deal is don't have any big global locks that block the entire faulting operation, because then the fault handling is forced to be sequential, and that's an easy way to violate the concurrency requirement of the assignment. There are a few subtle ways that you can do things, which I'll talk about. Hopefully I'll have time as I get through this sequence of slides. But, ideally, the important thing is don't hold one big lock that guards the entire fault mechanism. Disk interactions are already serialized. So this is part of it. I mentioned before, Pintos doesn't do any DMA transfers in the background or anything like that. Interactions with the disk controller are sequential, per device, I should say. So operations against swap are already serialized. Operations against the regular disk are serialized. And in all likelihood, you'll have other locks in your VM implementation that serialize IO operations for good reasons. So, you really don't have to think too hard about this. Think hard about it, but not, it's not going to make you lose sleep. The next lab, I hate to say it, but the next lab is the one that really is challenging on that front. Okay, extra credit. There is extra credit for this project. Implement shared memory support for read-only sections. So again, you don't have to think about read-write sections, only read-only sections. And if you do that, then you get a few points of extra credit for it. And you'll notice that the system call API for mmap and munmap in no way supports shared memory. There's no fork operation in Pintos. Like the way Unix works is you can actually memory map a file into your process's address space, and then you can fork, and the child and the parent both see that memory map file, and they can communicate by writing into that mapped address range. And so that's another way that dev0 is used, is people will open or memory map dev0 into their process, fork off a child, and now the parent and the child can use that address range to communicate as a shared memory region. You don't have anything like that to worry about in Pintos. So, if you feel like you want a challenge, try to do the extra credit, but don't fret it otherwise. Okay. Remember, we've been using this terminology for like 4 or 5 lectures by now. We have frames, which are also called physical pages in some discussions. These are actual chunks of physical memory, DRAM, on the computer that we can use to hold some data for some process or for the kernel. And as I say on the slide, for x86 processors that support virtual memory, we're talking 4 kilobytes. Now, there's other page sizes that you can do. There's also 2 megabyte pages and 1 gigabyte pages. We're not talking about any of that junk. We're keeping it super simple. 4 kilobyte pages, and everything is the same size. Then you have pages, aka virtual pages, and those are chunks of memory that a process cares about. So it's like a process's stack or a process's program or the data that the process is working with. So that's a virtual page. And the page will be in a frame if the program is trying to work with it. Otherwise, if the page is on backing store, it's not in memory, and if the program accesses the page, it'll generate a fault. And then the pager has to move that page's contents from the backing store into a frame and update the memory mapping so that the process can then actually work with it. So that's the idea of a page. Pages may be in backing store, aka swap, or they may be in a frame so that the program can work with them. Okay, and IA32 has this 2-level page table hierarchy, which we've talked about a number of lectures. So you have the page directory, and there's a special control register called, I think it's control register 3, that's used to store the page directory base register. And the page directory is just the top level of the 2-level hierarchical page table that is supported by the processor. And every process in Pintos has its own page directory so that every process has its own idea of what virtual memory looks like. That's how we build the address space isolation in Pintos. Okay, now you have swap slots as well. And I already mentioned these. We have a swap partition now. So you're going to have 2 partitions in your emulated Pintos disk that is used by the operating system. And the swap partition is chopped into 4 kilobyte slots. And each slot is just a place where you can stuff a page when it's not in a frame. Okay, and so as I say, now hopefully you all understand this notation. I'm going to be using it a lot today. There's a lot of circumstances where particularly marketing literature says, hey, this is a 1 gigabyte disk. And, I realize that's tiny now, but 1 gigabyte equals 1 billion bytes, or, 10, what is it, 10 to the 9 or something like that. And so that's a little smaller than if you're talking base 2. And so, one gigabyte, you would say, would be 2 to the 30, if I remember correctly. And so that's a little bit more than 1 billion. And so that's the reason for the I in these things. 4 KIB is 4 kilobytes. That's 4,096 bytes, as opposed to 4,000 bytes. Just in case there's any confusion, I just want to make sure. Usually when I say 4 kilobytes, I mean 4,096, because we're talking in real computers here. Okay, address space layout. Let's talk briefly about this. I know some of you have already been diving into this code. Pintos follows a memory layout for user processes that generally follows the IA32 Linux ABI, the application binary interface. It's laid out pretty much like I have here on the slide. There's a boundary between user space and kernel space at the 3 gigabyte or 3 gigabyte boundary, and that is where the constant fizzbase comes from in Pintos. Now, it's not called fizzbase in Linux because Linux does something different, but in Pintos it's called fizzbase because that's also the start of how the kernel is able to reference all of the page frames in the physical memory that are available. Okay. There are simplifications though. You'll notice Linux supports shared libraries. Linux supports user space malloc, which means that we need some memory break. That's what this BRK thing is right here. See, this has to do with virtual memory. Above BRK and below the start of shared libraries, accessing in this address range should generate a seg fault. Accessing below it may be abusing the memory heap, but it isn't. It is allocated memory. It's memory allocated to the process. So we don't have to worry about this dynamically growing heap in user space. And so we don't have to worry about these things. The only thing we have to worry about growing dynamically is the stack. So that's nice. And then all of these other sections down here, .text, .data, .ro data, .bss, those are all specified by the ELF binary itself, and you probably have already seen this code in process.c. Okay, Pintos has a constraint that it only will use up to 64 megabytes or 64 megabytes, if you will, of physical memory. Now, the IA32 page size is 4 kilobytes, so if you divide 64 megabytes by 4 kilobytes, you end up having a maximum, an absolute maximum of 16K page frames that you have to support. Now that's the total, okay? Remember that Pintos will divide this into a kernel page pool and a user page pool. So kernel pages can be drawn from that 16K pages, and user pages can be drawn from the these pages, but it's half. So you got 8K of those pages are used by the kernel, and 8K of the pages are available for user processes to use. Okay. I don't want anybody ever to hard code this 16384 into their programs. You should be referring to init rampages, which is initialized in start.s to the actual number of page frames that are initialized in the system. So you should be driven off of init rampages if you do this anywhere. Okay, so like if you're allocating a frame table of a certain size, you can use init rampages to compute what size it should be, and then iterate on palloc get page pal user to pull pages out of the user page pool, something like that. Okay. Major simplification, and like I was saying, Linux absolutely does not do this. And so, like I say on the slide, Pintos always keeps all page frames mapped into kernel space. Linux doesn't do this because it's infeasible to map the entire address space into kernel space, because if the entire address space is 4 gigs, because the computer has 4 gigs of RAM, You can't map that into 1 gig, but Pintos keeps all the page frames mapped into kernel space to make it super easy for you to write to any frame and to reference any frame. You know, you've got those V to P and P to V operations that move you back and forth. So that's the reason for that. Now I noticed that there's a couple of comments or questions in the chat. When I boot Pintos, it seems like the actual number of page frames available is only around 384. That would be really strange. I'd have to see precisely what you're seeing. Pintos, since it's running in QEMU or in Box, both of those emulators allow you to say how large the memory actually is. And so there is a particular BIOS call that's used in, I can't remember if it's in start.s, but I'm pretty sure it's in start.s, that it makes a BIOS call before it switches into protected mode to say, hey, how much memory do I have? And if the memory is larger than 64 megs, it gets clamped to 64 megs. So this 16,384 page frames is an absolute maximum. But it's certainly possible that the Pintos test harness initializes Pintos with fewer, a smaller amount of memory than that. So that's one possible reason why you may be seeing that. I'd have to dig into that more to see what you're seeing. Now here's another comment in the spec. It says, in Pintos, every user virtual page is aliased to its kernel virtual page. Does that mean all the contents of the user virtual page is also in kernel space? Yes, just automatically, because what we're talking about is a frame. The frame is holding the contents of the user virtual page for that process. And the fact that that frame is mapped into the user process's address space, and it's also mapped into kernel space at some address based on its frame address, means that you're going to see the same contents of that frame in 2 locations. The kernel can see it. The process will only see the frame as it's mapped into user space, because, of course, if it tried to access the kernel space frame, or if it tried to access the kernel virtual address, it would generate a protection fault. So hopefully that answers that question. Okay. Great questions. Yeah, so you can easily compute any frame's physical address. The one place physical addresses are used is in the page table hierarchy, because you have to be able to write the physical address into the page directory so that the MMU can do the address translation. That's the reason why we need these virtual to physical address translations and physical to virtual address translations inside the kernel. Okay. How do the page directories work? Well, there's a function in pagedir called pagedir create, and that initializes a new page directory for a process. And so you can think of it as working in this manner. Well, this is literally how it works. So of course you should think of it this way. There is an initial page directory that's created in init.c, and it's called init pagedir. And when it's initialized, only the kernel address mappings are set up in this page directory. So the way that I've drawn it here, you can imagine that the page directory base register points to the start of this page directory, and then there's some entries at the top of it that point to the address mapping for the kernel, okay? Because that's all we don't have a user process running as yet, okay? So we have that init pagedir pointing to an initial version of the page directory. Now, I want to talk briefly about this, because I want you to get more comfortable thinking about how these page directories and page tables work. I mentioned on here on the slide, on IA32, there are 1,024 entries in the page directory, because page tables, these nodes in the page directory hierarchy are 4 kilobytes. Entries are 4 bytes, which means, 4 kilobytes divided by 4, you're going to end up with 1,024 entries. Now you have 4 gigs of addressable memory. So in your page directory, you've got 1,024 entries. Each entry in the page directory corresponds to 4 megabytes of the address space. Okay, so you have a page directory entry that points to a page table, and that page table describes 4 megabytes of the virtual address space. I want you to make sure that you get comfortable thinking about these things. Okay? Now, as I say here, the kernel space boundary, remember, is at 3 gigs. So the top gigabyte is kernel space, and below that, the bottom 3 gigabytes is user space. So how many entries in the page directory correspond to kernel space? Well, if you have 1 gig of kernel space at the top of the address range, and the entire address range is described by 1,024 entries, then it should be obvious that a quarter of them, or 256 of the topmost entries, describe kernel space. Okay? So that's why I've drawn the picture the way that I have. Now, I also mentioned that Pintos only supports a maximum of 64 megabytes of memory. And so you could again say, okay, 64 megabytes divided by 4 megabytes, that's how many page directory entries I will actually have at max for the kernel address map. And so you really only should see a maximum of 16 entries at the top of this page directory that specifies the kernel address map. Okay? So hopefully you all followed that. Now, what happens when a process is started? There's a, this page dir create is called, and it makes a copy of the initial page directory. But it's a shallow copy. It only copies the directory itself. It doesn't copy any of the page table pages that are part of this mechanism. And so you can see here that when you have a thread that's going to be a process, it copies the page directory, and that page directory also points to the other page tables for the kernel address mapping. So it's not a deep copy, it's a shallow copy. Then, when you set up the address space map for the process, now configuring user space, you're creating new page tables hanging off of that page directory, but they're only visible from that page directory. And so this is part of how the address space map for each process can be managed independently. Okay, it's quite a clever little mechanism. Here's another picture where we now have 2 processes, and each process has its own page directory. And remember, we switch to that page directory in the thread switcher. That's part of dispatching when we schedule a new process. We switch the page directory, and you'll notice here, we're inside the kernel. The kernel can't change itself out from under itself. That would be disastrous. And it doesn't need to worry about that because every process's address map has the exact same configuration for the kernel. So all the processes share the same page table nodes specifying the kernel space map. If the kernel space map is changed, or if kernel data is changed within kernel space, that information, those changes will be visible from any process that makes those changes. So the kernel will always see its own coherent view of itself. If user space mappings are changed for a process, something's paged in, something's paged out, somebody calls mmap, munmap, that changes the process's user space map, but no other process will see those changes because of the way that this is all constructed. I really hope these pictures and these words clarify how this clever mechanism hangs together. If you have any questions, please put them into the chat. Okay, implementing virtual memory. There's a few key questions to ask yourself when you're trying to figure out what the hell am I supposed to be doing? So if you ever find yourself asking, what the hell am I supposed to be doing? Think about the part of the system you're trying to implement and what it has to be able to do. And then usually as you take those questions and answer them, the design falls out of it. So as I say here on the slide, most of the design falls out of answering the question, what does the page fault handler need to do? Because you might think to yourself, well, I may need to page out some other process's page, and I need to page in my process's page. Those are a few things I need to do. What do those steps require? Finding a swap slot for the processes page that needs to be swapped out, finding finding the information to put into the frame, finding a frame that I can use for all of it. So these are the questions you need to answer, and answering those questions generates the design that you need to follow. So is the faulting address valid? And if so, what data should exist at the faulting address? If not, you'd like to be able to say, hey, this is a bad faulting address, so I'm going to just kill the process. Okay? And so this kind of suggests how your supplemental page table should be implemented. Allocate a page frame for the faulting process to use. You're assuming you need a frame because you've assumed, you've already verified that the faulting address is valid. And if there are no available frames, which is usually going to be the case, it won't be the case at startup because you'll have an empty frame table, or I should say a frame table with no used frames. And also if a process terminates and all of its pages get thrown out, then you're going to have a number of frames that become available. So in these kind of situations, you might be able to find a frame easily, but usually you'll have to find a frame that's not being used anymore and evict the page that's in the frame so that you can make the frame available for the process to use. So you load the necessary data into the page frame. And so where does the data come from? Well, see question 1, what data should exist at the faulting address? Is it from a binary file? Is it from a memory map file? Is it stack? Is it read-write data? Okay, so you have to figure out, is it in swap? Do I need to pull it from swap? And then install the frame at the required virtual address. Okay, this tends to be the easier, like don't install the frame first and then write the data to it. That's a little bit iffy. So I definitely suggest you do it in this order. Ooh, a big question. Because all page frames are always mapped into kernel space, can a process in kernel mode access data in page frames used by other processes as well? The answer to that question is yes. And this really well illustrates why the kernel should be viewed as a trusted intermediary between processes and other processes and the hardware. It turns out that even a kernel like Linux, where not every page frame is mapped into the kernel's address space at any given time, the kernel can still do whatever the hell it wants. And so it could say, you know what, just for funsies, I'm going to access this frame over here and like push it out onto the internet somewhere. It could do that if it wanted to be a jerk. And so kernels are totally supposed to be trusted intermediaries, and you can sort of see why it's really important to have trusted operating system implementations. That's why I like open source so much. But yes, in Pintos in particular, it's very easy for any process trapping into the kernel can see all the process's data all at once for sure. Now let me see, there's another question. Even though all page frames are always mapped into the kernel, pages are only taken out of the user kernel pool when we call palette get page. Yes, that is also correct. In fact, that's the way that the virtual memory implementations of virtually everyone work, is that they claim all the page frames out of the user page pool at initialization time, and then they manage the assignment and reclaiming of pages that were in the user page pool from that point forward. So hopefully that helps. Okay, let's see. Page fault handler will often block on I/O. And this is another thing that's worth mentioning, because you might look at this and say, wait a minute, I'm in an interrupt handler and I'm blocking on I/O. And so what context is this interrupt handler running in? And the important detail here is that the page fault was caused by a user process, not intentionally, but inadvertently. And so you can view the page fault handler as running in process context. That's the right way to understand it. And so you can think of this as being a second way of trapping into the kernel, just accidentally and transparently to the process. It doesn't, ideally, it doesn't even know that this is happening. So that's just an important little detail there. Okay, so yes, other processes should be able to run. The page table, the page directory information used by the processor's MMU simply doesn't contain sufficient information to implement the Pintos virtual memory. And so this is why you need a supplemental page table to build this virtual memory abstraction, okay? And so what this means is that every process is going to have a supplemental page table along with the page directory that's set up and used by the MMU, okay? Or for the MMU, I should say. The MMU doesn't set it up, it just references it, okay? And so you need to think about all the details that are necessary for the OS to do the magic that it's supposed to do, okay? The supplemental page table should describe the entire user address space of the process, not just what is currently paged in, because you also need to know if something is on the swap device and that the address range is in fact valid. We just have a fault, and we can get the data from swap if we have a fault in that address range, okay? It should be fast. And so this is why the design guidance is use a hash table to represent the supplemental page table, hashed on page number, or maybe, you know, like the virtual page number, not the physical page number, because that'll change. Or you could use the starting virtual address of the virtual page in the address space if you wanted to do that. I mean, they're going to be the same, just one has more zeros than the other. Okay, so more questions to drive design. Where does page data initially come from? There's basically three places that page data can come from. You have binary program data, so that'll be your .text, which is read-only, .data, which is read-write, .ro data, which is read-only. That's what the RO stands for. You have, yeah, like I say, some of these are read-only, some are read-write. And so when the read-write portions of the binary change due to program execution, do not write them back to the binary. That's a disaster. It needs to go to swap. You have the anonymous file, which 0 initializes memory. And so this is what stack pages would do. Now, you may not implement a specific anonymous file like exists on Linux or Unix, but you'll just have a ring, you know, this needs to be zeroed, or this needs to be pulled from this file. So you may notice in the initial implementation of process.c load and load segment, or whatever it's called, it's got read bytes and 0 bytes. And that's a great way to think about what information needs to go into the supplemental page table. BSS should initially be all zeros. So BSS would be pages whose initial contents are zeroed. And as I say here, BSS is an interesting section in ELF binaries. It's described, but there's no actual file data for it because the intention is that it is 0 initialized. And then you have memory map files, which of course you call mmap, and that sets up the address mapping in the process. And then when those addresses are accessed, it generates a file access behind the scenes, okay? So these are the three places that data can come from. Now you have the question of where is it evicted to? And again, this varies. And so this should help you to figure out what information needs to be in your supplemental page table. If you configure your supplemental page table entries properly, then your page fault handler can just be very mechanistic. Okay, I need to page it in. Data comes from here. I need to page it out. Data goes here. It just follows the sort of the instructions that are set up at initialization of the supplemental page table entries. So you have binary program data. Where is that evicted to? Well, never the binary file. That's the answer. Read-only sections can be thrown away because you could just load the contents again from the binary file. Easy peasy. Read-write sections need to go to swap. If you have anonymous file or 0 initialized memory like your stack, then that shouldn't go to any file. That should go to swap. Memory map files, well, those should go back to the data file, okay? So fortunately, again, Pintos doesn't have the notions of copy on write or read-only objects It only knows about public shared objects, and it doesn't even specify any semantics about how it should behave across processes. So you can always write memory map file data, as long as it's not the original binary, you can write that back to the file, okay? And if a page is saved to swap, you need to remember the swap slot. That should be sufficient for designing your supplemental page table entries. Okay, so yeah, these are all the details you need to track in your supplemental page table. And by doing so, when your fault handler goes off, you can get that faulting address, round it to the start of the page, do a lookup against the process's supplemental page table. Oh, there's nothing, you're dead. You kill the process. Oh, it is something. Well, now you know what to do for the next steps. Okay. So when a page is being evicted, it should make it easy to decide where the page data should be saved to. And this is something to think about. Process A faults. Process A needs something paged in. The pager says, here's a frame, but it's process B's page. So we need to update process B's information to evict the page from the frame before process A can assume ownership of the frame. So this is the thing. When you're paging things in and out, you actually have two processes that may be involved. And so you need to think about what the pager needs to do on behalf of both of the processes that may be involved. Okay? All right. Frame allocation. The handler has to find a frame to hold the page being loaded, and so the OS needs to know somehow how many frames are available and which ones are in use by processes and so forth. This is the purpose of the frame table. And like I say, if no frame is available and the OS has to evict a page to free up a frame, it needs to know what process was using the frame. And so this is all what's supposed to go in the frame table. Again, the operations required against the frame table entries drives what should be in the frame table entries. That's why in some of the discussions I've had with some of you, I've said, yeah, you kind of need to know what process is currently using the frame table entry. You need to know the user virtual address of the frame, the user page that's in that frame, so that you can go and update that process's supplemental page table when you evict the page from the frame. And you probably need a lock as well to guard the frame or to pin it when you're doing these longer running operations against the frame. Okay, so the suggested order of implementation, and this is just what is in the assignment write-up, but hopefully this discussion will help you understand why. Implement the frame table first. So you just, instead of having pal get page pal user, you have something that goes and grabs all the user pool pages and puts them into your frame table and somehow keeps track of which ones are available, which ones are in use. And then you use your frame allocation code from process.c. That's the first step here, okay? So ideally, you get this working and nothing else is changing. You're not really doing page faults or anything like that, except when there's errors, and you get your test passing. Okay, so like I say, swapping and eviction don't work, so you can panic if you run out of frames, and then you try to make sure. Now, I have to say, as a caveat here, there may be Project 3 tests that stop passing. There's like a few that are actually sensitive to virtual memory. So if you run into any questions, please ask me or ask Hale, because there may be certain tests that actually do fail as you go through this, but it should be few and far between, just for the sake of clarity here. Okay, then you implement the supplemental page table. So you set up your supplemental page table entries, recording what should go in each page, but you don't actually load it. You set up your fault handler to load. So basically what you're taking is some of the code was in process.c to load the contents of the virtual pages into the frame. You're moving that now into your fault handler. So you're kind of refactoring a little bit, okay? And so then you can go ahead and you do the lookup against the supplemental page table. Is it a valid access? If so, pull the data that the supplemental page table entry says to pull, okay? So as I say here, you still don't have eviction. So when you run out of pages, or let's say when you run out of frames, panic. Okay, that's what the suggested implementation is. And then you do your best to try to get all the tests passing. There may be a few that are sensitive to this, but you get as many passing as you can. All right. Question, where should we add pages to the supplemental page table? There are 3 things that modify the supplemental page table. Program load, because you're scanning through the ELF binary sections, and that says what parts of the address range are valid. So that'll update the supplemental page table. When the stack falls out of the current page into the next page and you need to add pages to the stack, that will update your supplemental page table. And when mmap and munmap are called, that will modify the supplemental page table. Those are the 3 operations that modify the address range, or the virtual address mapping, if you will, of the user process. So those are the 3 things that modify the supplemental page table. No malloc, no shared libraries. Whew. Okay. Let's see. From this point, you can start implementing things in parallel. So you can see that those first 2 steps are kind of crucial to get working in sequence, because it just sort of makes things easier. And then you can branch out and start implementing some stuff in parallel. So stack growth, memory map files, reclaiming pages and swap at exit, and so forth. You do need to implement page eviction, and a lot of people start with a simple policy. I think that the simple policy that's recommended by the assignment is simple enough to just start with. And so I might even just start building that from the beginning and then build out the full implementation of the policy without doing something interim that is like, it sucks. The one thing that we've seen over and over through the years is students say, I know, I'll always evict page 0, or the page that's in frame 0 is really what I should say. That is a terrible idea, because basically you hammer on that 1 page frame over your whole computer memory for Pintos appears to be 4 kilobytes. And you will want to shoot yourself in the head. So don't do that. Even a random policy would be better than that. And actually, to be honest, it would be much better than this kind of an approach. But why not just go for the real thing? Why not just go ahead and implement clock, as or the first parts of clock, so that you can carry on from there? Okay, so you have to approximate LRU somehow, and clock is what is suggested. And the beauty of clock is you don't need to use any kind of timer interrupt for clock. And so what you should do is just start with an index, which is the clock hand, and move your clock hand through the frame table. Okay, you can start it at frame table entry 0, and when you need to evict, you can go ahead and advance it and look to see if that frame table entry is available. Now, when the entire table is unallocated because no processes have run yet, that'll be easy. You just move through it and you can acquire more frames. Now, at some point, you're going to hit the end. You could just panic initially, or you could wrap around and you could continue through. And so it just becomes a matter of slowly building out the different parts of clock to properly implement the policy. Eventually, what you'd want to do is look at the page table entries, the frames page table entry to see if it's been accessed. And if it has, clear the access bit and move forward. You also have pinning to incorporate as well, but that's why I say start with an index, and you'll be one step closer to having clock implemented. Okay, you can do other more sophisticated things, but only if you really want to. I certainly would just implement clock if you just want to survive this this assignment, because it's a pretty challenging one as it is. That's what I'm trying to say. Okay, last thing to talk about is concurrency and synchronization, and we'll go a few minutes over the normal ending time just because this is a bit complicated. There are long-running operations that can occur passively in the background and should allow other operations to continue. So you'll notice that you have scanning to find a page frame to use, scanning through the frame table, scanning to find a swap slot to use. Okay, you probably don't want two processes interleaved in the kernel scanning through the bitmap for the swap. Because what if they find the same swap slot? Then you've got disaster. Okay, so there's certain, you just look at this and you say, I'm going to guard this with a lock. I'm going to guard this other thing with a lock. And then, you have synchronization. There's, just keep the concurrency requirement in mind. IO bound faults should not block non-IO bound faults. That's really all you have to worry about, okay? And like I say, it shouldn't be too hard to satisfy this requirement. Just don't have anything holding on to a global lock through the swap load or swap save or write a file back to disk type operation. Okay, so let me see. I'll try to wrap this up as quick as I can. Yeah, you can do this entirely using locks. You don't have to do any fancy pants stuff. The only thing I'll say is if you do implement a timer-based page replacement policy, i.e. you use the timer tick handler to do anything special like aging or an ARC or CAR type policy, you will probably have to disable interrupts in a few places to build that. But if you don't, you can just use locks in your implementation. Okay, so like I say here, you may have locks guarding larger operations like scanning the frame table, scanning the bitmap that tells you where swap slots are available. And it will limit concurrency, but it satisfies the assignment requirements, so just freaking do it. There is one situation that you have to think about that is a little bit complicated. You have process A, just to give you the scenario, faults on its virtual page 25, and you need to evict some other page to make a frame available. So the kernel picks a frame, and it happens to be a virtual page of a different process. And so the kernel starts writing that page's contents to swap. And so that suspends process A and switches to process B. Now process B starts to run, and it tries to access the same virtual page that's being swapped out as part of the swap operation for process A. This is a complicated one. So the question is, does your pager fault? Yes, no. It's okay for it to fault. And if it does fault, how is that handled, since you may still be writing the contents of that frame to swap or to disk, and the page in operation could leapfrog the page out operation and you could miss out. Now, it turns out that probably because of the way the disk works, you'll be okay because they're serialized. So you may not have to be very clever in this situation, but it's something you have to think about. And if you want to be super clever, I would probably be thinking about putting locks in the individual supplemental page table entries. There's dangers and risks associated with that. So it may be that a good design falls out of the fact that accesses to the device are serialized anyway by the device, the block device implementation. So you may actually be okay. But these are the kinds of things you'll have to think about. And this is the kind of thing that the design document is going to ask you about to see, have you thought them through? Okay, let's see. The last thing, helpful to incorporate locks into page frames. This is a great idea because you can implement pinning of frames using the Pintos lock mechanism. There's lock acquire, which blocks. There's try lock acquire. So like your eviction, when you're trying to implement your eviction code, you can basically try lock acquire the frame that's under the clock hand. And if try lock acquire fails, move on. Means it's pinned. Okay, so you can implement pinning really easily with the lock mechanism. Lock held by current thread. You can find out if you're the one who has that frame pin. Okay, so you can do something like that. Okay, I think that's the last slide that I have. A few more notes. Yeah, definitely want to follow a modular approach because this implementation this project is an absolute nightmare to debug if you build all the parts at once. So don't build all the parts at once. I hope you haven't already started that way. If you have, CS124 is one of those sad face classes, sad panda classes, where like sometimes there's bugs that you can't find and you just throw out your implementation and you rebuild it from scratch. Like it hurts me inside when I hear that, because I'm always like, let's try to find the bug and fix it. But I've had so many students who have encountered that through, I've been teaching this for over a decade. And sometimes students just say, you know what, I can't figure out, there's something I don't understand. They throw it away, they re-implement, and it works. So I'd like you to avoid that by following a modular approach from the beginning, but sometimes, sadness happens. Anyway, so hopefully this will all help. We wish you the best of luck. And of course, Hale is going to have some weekend office hours. I'll have my office hours next week. And if you have any questions, please get on Piazza, get on Discord. We'll help you as quickly as we possibly can. And we wish you the best of luck. So we will see you next time.